Hey everyone. Hey everyone. Um, there you go. Haha. Okay, so thanks for coming back. This is part three of our gradient descent for linear regression in Python. That's the main screen. New image. I make an image for every one of these videos using Midjourney, by the way. I plan on doing something along the lines of a little tutorial or whatever about that at some point in the future. So if you want to see that, if you're excited about that, just let me know. I would love to show you that. But getting back to this, before we start, I just found online. Actually, I look up machine learning like tutorials and resources and stuff, and I was actually looking up like free materials today, and I came across this book, which is totally free, and the link for this is in the description for this. That could be really helpful in your journey if you're trying to get specifically into machine learning. And a lot of the things I'll be covering in this series are going to have like some overlap. You can see here what machine learning sort of includes. So in this series, we're going to be talking about a lot of these topics. Definitely we'll be talking about supervised learning. We'll be talking about unsupervised learning probably towards the end, but we'll definitely get to that as well. And then reinforcement learning as well. There are going to be some topics in deep learning, which is kind of a subcategory of machine learning that we'll get into eventually as well, specifically with PyTorch, but that'll be much further into this series. So yes, if you're curious at all about like machine learning and you want like a little book that you can have with you that you can take and you can read on your own time, this is a great book. Another great book that you might find helpful is Data Science. I think it's called Data Science for Python. Yes, Python for Data Science. So this is not in the. Actually, I'll go ahead and pop this into the links as well. But the name of the book is called Python Data Science Handbook. This is a really great book too. Now, this won't necessarily cover the things specific to machine learning, but data science is one of the fields that are like sort of adjacent, really important for machine learning. Basically, where this fits into it, structured data. So we're talking. So yes, these two resources I would recommend. This is actually the book that I have, Python for Data Analysis. Another great book as well. So yes, go here, but you want to take this material and make it your own, and the return on interest is big, very bigly. So anyways, back to this. I just wanted to make that small caveat. I'm going to continue to expand the links for the resources in the stream video. So I'm gonna actually pull up here. This might look weird, but if you see how I have like this resource section here in the stream, this list is actually going to continuously grow as I go from video to video, from stream to stream. So just keep checking back here, for resources and links, whatever I find helpful. I'm going to put it there mostly for myself, but I want to invite you to go check there as well. Okay, so back to this. When we left off last time, we were having some challenges because our gradient descent function, whenever we were calling it, it was not doing what we were expecting it to do. With a friend to go for a walk, and I totally forgot, so I had to sort of leave the stream. But I didn't want to do this off camera because I think this is a really important process to show, to be comfortable with doing. And so, as awkward as it might be, I'm willing to go through this awkward process with you. And now, this isn't to say that I know what the problem is right now, but that I'm just willing to do that so that you can participate in that. Okay, so now I'm going to bring over my other screen here because I want to be able to kind of show the difference between what I have going on and what I am expecting to get. So even though these lines are different line numbers, This is basically the same code here. This is the code that's provided by just like on separate lines so that it's not this big long, big long line. I'd rather have them like sort of spaced out for visibility. But that's the only difference here. And I think the comments even are the same at this point too. So when I run this line here, actually I gotta run the whole thing so that all the variables are initialized. It's gonna take a second. I'm actually gonna run all of mine too. So when I run this in this example provided by the course, you can see here that I get all of these different iterations, and these iterations contain the history of the cost and the and for each of these histories there is a cost in relationship to, there's a cost, a derivative of the cost for the weight and for the bias. Basically, that's what these two are here. And then there is a history, the parameter history, and there is a, we actually set that, oh, this actually should be 10,000. So we actually set that here. So there are 10,000 iterations that happen, and they're grouped. Oh, you know what? That might actually be the problem. Maybe it should be 10. Let me refresh. Let me refresh this because I might have messed. That might be the problem. I might have actually accidentally hit a button unintentionally. Let me refresh this lab. Hopefully it doesn't save that state. Okay. Okay, yes, 10,000. So there's 10,000 here. Let me just be ultra sure. And I'm gonna open up a, let's see. I'm gonna open up a new window here. Just give me 1 second. I actually want to just reopen up this learning session, and as you can see, I'm a little bit behind here, but I'm going to reopen up this assignment window. Oops, that's the wrong one. Here we go. Reopen up this lab, and pop this over here, close this one. Okay. And apologies if you're hearing like some noise in the background, because there is a street and sometimes the drivers are very ignorant. I can't help that. Okay. Okay, now this is basically a fresh session. I just want to make sure that there are no weird things that I copied or whatever. Okay, so it turns out that this actually should have been 10, and I think that's because it's matching what they have here, which is these intervals. So I had 10,000. I don't know why I did 10,000 in my copy here, but I'm gonna see if that fixes anything. It did not. Okay. Okay, so what I'm gonna do is I'm gonna start here at gradient descent, because I'm pretty sure that my compute gradient works. I'm pretty sure that this works. Well, actually, it wouldn't be a bad idea to kind of walk through all of this. Let me just start here at compute cost first then. So it forces me to understand those nuances when I have to go back and like, look at things closely. So passing in our 4 arguments, x, y, weight, bias, and then we're getting the length of the x training data. We're associating that with, we're assigning that to the m variable. Then we're setting our cost to 0 because that is our data structure that we're going to use for summation to hold the summated value of our squared error, cost error. So for I in range m, this is the linear regression function here on this line. So w times x of the index plus b plus bias. Cost equals cost. This is our summation here happening. Cost equals cost plus parentheses the linear regression function. This right here is basically going to give us a prediction and then minus the target. The target is coming from our Y training data. And then we're going to take this whole thing, before we add it to the previous cost of the iteration, we're going to square that. And then total cost, which is, oh, I think I see something wrong here. This is tabbed over, should not be tabbed over. So the total cost is going to be created as a variable at the end of this loop. Excuse me. At the end of this loop, and it's going to take the summated cost and it's going to multiply it by 1/2m, which is basically dividing it by 2m. I'm going to run this here with the new correction, and I'm going to go back and run this one. I'm going to run this one and this and see if that fixes anything. It did not. I'm going to also run all just really quickly. Okay. Well, that was one error that I found, so that's nice. That lets me know that there's probably just some small things going on here. I'm going to check my starting data structures too. My little arrays up here. Okay, those are good. Okay, I think compute cost is fine. Now we're going to check compute gradient. And you can see, by the way, I'm not just copying the notes directly from the course here. Typically, at least, that's not what I do. I'm actually putting things in my own verbiage and whatnot. Because the point of taking notes is for you to understand it. And you're going to have your own style and flavor. That's just my little tangent there, but that's important to recognize here, is I'm not just copying things over. I'm trying to take my own liberty and my own approach to things. It helps you understand better. Okay, so we have our compute gradient. Okay, so the first thing we do is we're going to get that size for the X training data here. And then we're going to create data structures. These are just going to be scalars. Actually, I forgot to put the comment there. Scalar is just one value. It's going to be a magnitude as opposed to a vector, which is a magnitude and a direction, which is two numbers. So that's what this is here, the gradient cost in regards to the weight, gradient cost in regards to the bias. And these are going to hold like that iteration over each of these. And these are going to be updated simultaneously. That's an important thing. So for I in the range of m, the linear regression function equals weight times x at the index plus b. Okay, so that's correct. So we have these derivative cost functions for weight and bias that are occurring at the index. They're occurring at the index, and oh, sorry, I didn't have my music playing. They're occurring at the index, and we're storing them in these two variables here. So with regards to weight, it is the linear regression function minus, so it's the prediction minus the target, and that's both in parentheses, times the X training data at the index. And then for the bias, or the derivative of the bias at the index, it's the linear regression function minus y at the index. Okay, and then down here, this is the updating. So this is adding the new, so we're taking, at each step, we're performing this derivative function here, this derivative equation. And then after we do that for both the weight and the bias, then we're going to update these two here, these two weight and biases. These are stored outside of the loop. So for the derivative of the cost with regards to the weight, I can see something I did wrong here actually. Wait, no, that's right. I just have these inverted. I don't think that will matter though. I don't think the fact that I do these in the opposite order matter. But just for kicks and giggles, I'm going to put them in the same order as they are in the example, just to reduce the difference. So dj underscore db plus equals dj underscore db underscore I. And then same thing for weight. Okay, so then we're going to step out of the loop. Then we're going to update the derivative cost and divide it by m for both respect, or with respect to both the weight and the bias. Okay, so that's right. Everything lines up beautifully. Compute gradient. Okay. And then finally, we're going to return the derivative cost of the weight and the derivative cost of the bias. And these two here, these are going to be the minimum. So these are not just regular, single applications of this gradient function. This is the minimum after all the iterations and steps. No. This is one. This represents. This represents one step along the entire range of m, and then this gradient descent represents this here, but done towards the minimum. That's how it works. Okay. So the next thing here is we have PLT gradients. This is a function provided to us by this course up in this like utils uni thing, lab utils uni. So that's out of our control. Literally just copy or save that file and put it into my environment. So we're passing in X train first, Y training data first, compute cost, compute gradient, and then PLT dot show. Let me just run all of these because I think I forgot to do all of them before I got it on there. Okay, so everything's fine, everything's Gucci. All of the diagrams here look the same. That is pretty significant positive. So I'm expecting to find some type of issue now in this gradient descent function. And if I don't, I'm gonna be a little bit confused. But let's just check it out. Okay, so first I'm gonna check my arguments here. So we have our X. Okay, slide over. No, okay. So we have our X training, Y, and we have our weight. What does this mean again? Oh, okay, so W and underscore N and B underscore N, those are initial values of the model parameters. That's where we start in our gradient descent. We start with some type of assumption that we work from. So that's what these two are, WN, BN. And then alpha is going to determine how small the differences are between each of those iterations. Okay, so num iter. I remember I was like doing this wrong with like the plurality. So I'm going to make that match, which I'm going to have to fix down there as well. Cost function and then gradient function. That's next. Okay. If I were to run my code right now, I expect an error because, yeah, see, I expect this error. Because this is not plural anymore, so that's like expected right now. Okay, so the next thing here is we're taking the weight and we're making a deep copy of the weight that is coming in as the initial value. This deep copy basically means that we're taking this entire data structure that we're passing as an argument and we're going to recursively duplicate it into a new variable. There are aspects of this data structure that are not apparent to us. All we really care about is the value, but there are other things that come attached to a data structure too. And that's what enables like the functions and methods to be called on if they're like built into Python or whatever, or built into NumPy. But what matters here is that we're doing the same exact thing. So we have copy.deepCopy, and then the argument that we're passing in is the weight, initial weight. So here, avoid modify global. Okay, so the next thing here is we create variables to store the history. These are lists and also for parameter history. And then we're creating the variable for, now this is a part that I did not understand. I'm just gonna leave a comment here. I don't understand exactly why the weight variable is overridden when we define it up here. I don't, it's a little confusing for me. Yeah, I'm not really sure, to be honest. I think maybe what this does here is that it makes this weight into a data structure that is the same as this here, so that when it's reassigned, it has the typing associated with it. That's my only real guess right now. But like I said before, what matters is just that it's the same. So for now, at least. Okay, so I need to make sure this is num iters. So for I in range num iters, this is a number of iterations that this is going to go through, which I think will be like 10,000. Or it will be, yeah, it'll be 10,000. Okay, so then we're going to calculate the gradient, update the parameters. So these two are being destructured off of this gradient function, which has the arguments of x, y, w, b. Gradient function, okay. Make sure that these are in order from where, w, okay. Cool. Next thing is that we're taking the weight and the bias, and then we're performing this. This right here is the gradient function. So the gradient function is the weight. This weight is going to be updated with each iteration of this loop. So we're going to take whatever the most recent weight is. We're going to subtract this. We're going to subtract the product of alpha times the derivative cost of our function with regards to weight, which is this here. I'm actually going to, similarly as I did before, I'm going to change the order so that it is the exact order that we have in the example. I don't think that should make a difference, but just in case there's some weird thing that I'm misunderstanding, I'm going to do it. There's been weird, obscure things before in programming languages that I've like glazed over. I don't want this to be one of them. Okay, so first is the bias. Bias equals bias minus alpha times the derivative cost of linear regression function with regards to b. Weight equals weight minus alpha times the derivative cost of our linear function with regards to weight. Okay, so save cost at j for each iteration. Okay, so if, make sure everything lines up here. Okay, so if the index is less than 10,000 or 100,000 rather, Yeah, if it's less than 100,000. Wait, I think that, wait. Let me run this real quick. I'm getting ahead of myself. Okay, slow down. I think I might know what the issue might have been, but let me just keep going. Okay, so this will prevent resource exhaustion by setting an upper limit to iterations ran. Okay, that's what this means really. Okay, so our cost history, we're going to take that cost history list here, and we're just going to keep appending our cost function. I believe that this cost function is a vector. Because it has two. No, it's just it's a scalar. Okay, so it's going to be one number. So we're going to be appending each of these cost function results to this cost history list every iteration. We're also going to be appending this parameter history, which is a vector because it's going to contain a list. It's going to contain a list of two. It's a two-dimensional array, which means that it's a list that has lists within it, and each of those lists within it have two numbers associated with it, and it'll be the weight and the bias. Okay, so the next line here, this is what's going to be printing our results. Now, the printing of the results, I think that's where our issue is, but we're going to walk through this. So if I modulo math.ceiling, what does math.ceiling do? Okay, so it's going to round a number up to the nearest integer. Okay. So if I modulo, I'm just going to make sure I completely understand that. Modulo obligato. Okay, so when you do, I'm just gonna actually make a line down here at the bottom here, just 5 modulo. What does that return? That's like not good syntax. Oh, I need to have another number. Math.ceiling 10,000 10 5 Okay, so this is just going to divide. It's going to take this here divided by 10, and then whatever this would be, because this number could change, this number of iterations could change, it's going to divide that by 10 and round it up to the nearest integer. And then what we're doing is we're taking with this line up here, so it'll be 5 modulo 10 or modulo 1000. I'm not sure what that means. What does that mean again? I feel like I should know this, but Modulo obligato. Modulo obligato. So I think what this is doing, right here where it says if I modulo math.ceiling number iterations divided by 10, I think what this is doing is saying that if you take whatever the iteration is and you divide it by every 1,000 iterations, it'll print. So that's what's happening here. That's what that means. So if the current index, since it's going to do this up to 100,000 times, we're only going to do 10,000, but it can do it up to 100,000 times. If the current iteration is at a number that is divisible by 1,000 with a remainder of 0, then it's going to print a new entry for our little print console here. That's what that means. Okay, cool. We got that. Gucci, we're fine. Are you Gucci? Are you good? Are you Prada? Because I am. Okay, so I'm gonna go ahead and delete that cell now. Okay, I know it's laborious, but these are the things we have to do to learn. Okay, I'm going to add some space here. Just give me some space to breathe. Okay. Now, this next section of code here, this is what I have, this is what this is right here, and next we have this printing. So we're going to do formatted printing, and we're going to print multiple things on the first line here. So these are matching up with this basically here, So we have F parentheses or quote iteration. This here is going to take this number, the number of the iteration, which will be like 1,000, or it'll start with 0, but it'll be like 1,000 or 2,000 or whatever, and it'll make sure it's padded by 4. So that's what this is doing here. Okay, and then it's going to take the cost here, and it's going to write this out in scientific notation. This J history with the -1 being passed into it means that it's going to take the last entry for the index. It's going to take the last index of this list. Since this list is going to have like 1,000 entries in it per print, like 1,000 new entries, we only care about the last one because that represents the most recent state. So this -1 will do that for us. And then this is scientific notation formatting here, this 0.2e. So that's going to be inside of a curly bracket. Okay, and then comma. Then we're going to be formatting the derivative costs for both our weight and bias here. So dw, colon, this is scientific notation, comma, and then bias here, bracket, there we go. And then more scientific notation into these quotes here, make sure my quotes match up. And then we're going to go to new line, and then we're going to be printing out the final weight and the final bias after all of this is run, after our gradient descent has run. We will have settled on a local minima, basically. There's gonna be multiple ones, but there's only gonna be one minimum. But like more advanced functions, there's potentially more than one minimum, and it depends on where you start your gradient function, gradient descent function. So this is gonna be the final based on this, and it's W, and then we're formatting it and signing. Okay, I think that's good. And then at the end of this, we're returning our weight, bias, cost history, and then parameter history. And I think that one thing I didn't do correctly here is this is tabbed wrong. So that, I don't know if that matters, but yeah, that is definitely not how it's supposed to be. So, okay, I got that fixed. Now, here, oh wait, I think I might have missed, this should be iters. Okay. Ooh. Okay, there we go. Does that run now? Perfect. Bam. Hey. I get so excited when things work. I just want to do a dance. I gotta get some dance music. I gotta get like a little thing where I can like push a button and get the lights flashing like that, and just be like, we're gonna get that figured out one day. I just don't want to get a copyright strike for playing some house music or whatever. Gotta get the right color back. Okay, there we go. 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 Okay. And okay, before we get too excited, let's just make sure our numbers match up because we don't want to, look crazy out here. Okay, so the cost 7.93 to the fourth power. Okay, cool. 7.93 to the -1. Cool. Okay. And then our fine. Okay, cool. We're back on track, y'all. We are back in business. We're back in business. Okay. Now, okay. So what I did here, now that we're back on track, is now I know earlier I was talking about all this mad stuff about how I like to do my own notes and everything, customize them. But since we're a little bit behind on this, I went ahead and prepared the notation part of this, like the comments and everything, so I don't have to do all of that right now. All we have to do is really just read through them and then plug in some programming, because this is the last video I'm gonna do for this. And I don't even know if I'm gonna get to like a review video, because I really have to move on with my course, and I think I've just done enough explaining. I might just save it for later, really, I don't know. But I just know I wanna get through this right now, so we're gonna just blast through this and try to get this done. Okay, so next we have to do, it says here, a plot of costs versus iterations is a useful measure of progress in gradient descent. Costs should always decrease in successful runs. The change in costs is so rapid initially, it is useful to plot the initial descent on a different scale than the final descent. In the plots below, note the scale of cost on the axes, and the iteration step. So I'm gonna just plug in the code to make that work as described. Okay, so we're gonna plot cost versus iteration. So basically we're doing 10,000 iterations, and we want to basically see a comparison from like iteration to iteration. How does that influence the cost as that cost is going down and as the two parameters are converging towards one another? And then the cost is going hopefully towards minimum. So first part of this is, now there are some things that I'm going to be using from that utility package that's provided that I don't have the luxury right now of breaking down and getting into. So there's gonna be a little trust here involved, a little trust fall. All arguments here. I don't know what all this means, but we're gonna do it anyways. Constrained layout. This is probably just like some formatting stuff. I think that their little utility thing is just used throughout this course, so it's not, you know, specifically limited to being used in this module. Okay, 12.4. So fig. Ooh, that was loud. Sorry, people outside have loud cars. So fig, and then AX1, AX2 equals, or yeah, it's coming off of this plt.subplots. First argument 1, 2, constrained layout equals true, underscore layout equals true, and then fig size 12.4. I'm not sure what all that means, but that's fine. AX1.plot, and we're going to plot the cost history. This is how we understand like the relationship between cost iterations. So this matplotlib stuff, it is important, but not for what we're doing right now. Some of those books I was showing earlier about like the data science in Python, those would be the places where you could learn a little bit more of the nuanced information about what matplotlib is doing, matplotlib and NumPy. Okay, so I'm missing R. Oh wait, no, that's fine. A range, and then length. Len is the length function that's built into Python. J, so this is the cost history. Ooh, these cards are a little loud. I need my headset with my little microphone. I hope y'all can't hear the cars outside zooming past. Like, it's really distracting for me because how my brain is built. Okay, cost history. Actually, let me go ahead and just like pop this stuff in here because, like I said, I don't think this matters for what we're doing exactly. Okay. So this is the start. Okay, so what this is doing is breaking up the iterations. Since there's like 10,000 iterations, this is this right side. This represents the entire. It looks like all 10,000 iterations, whereas the one on the left side represents the first 100 iterations. So these are kind of the same. It's just that this is more inclusive of the entire operation, whereas this is just a subsection. So we can see that as we start from the beginning of our gradient, the cost is decreasing as it converges towards 0. And it's decreasing quite fast. Whatever the opposite of exponential is, I don't know if I know that term, but whatever that opposite, that's what it looks like here. And so at first, you can see here at first, these changes are happening at such large increments at every step. And as it moves down, as it goes through each of these iteration steps, the changes become smaller and smaller and smaller as well. So big change, bigly, small change, smaller, 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 until it converges towards the lowest cost. And then by the time it gets to the lowest cost, there's not going to be any change in the cost. If it's 0, it'll stay at 0, of course. The parameters will stay the same, whatever they are at that point. And if it's like some other number, it's just not going to decrease anymore. And if your alpha was too large, then you actually might see divergence where this line might even go back up like a parabola. In which case you know that your settings for alpha are too large. I think I might have mentioned that before, but that's one of the risks you take when you're figuring out what the alpha is. Okay, so the next thing we're doing is, now that we've discovered the optimal values for our parameters, which are going to be these two here. So weight is optimal at this number, and then bias is optimal at this number. Now that we've discovered what those are, we can use this model to make a prediction for the house values based on that training data. So we can take our function basically, and let's see here. Yeah, we can take our weight final, and we can multiply that by some number of square footage and then add our bias to it, and that will give us a prediction. Because, okay, so I'm just going to go ahead and take what they have here. This line here, by the way, this is our linear regression model. This is the weight that we've determined from our linear regression, or from our gradient descent, which is this right here. We're taking that number and we're multiplying it by some square footage here. And then we're going to add our bias to it. So remember that linear regression function is the weight times some x plus a bias. And then that, anyways, this here is a formatting. This is why I recorded these streams at nighttime, by the way, or like really early in the morning before like traffic and everything, because it's just much easier in terms of sound quality. So this is just the formatting, because these are gonna be very large numbers in the hundreds of thousands, and this is just going to reduce them to like a smaller number. So when we run this, we should get like 300, 340, 500, and then these are equating to like thousands, of course. So you can see here for $1,000. And so just to compare, when we initially were setting up our data, we were getting like $1,000 house is 300,000 square, I'm sorry, 1,000 square foot house is $300,000. 2,000 square foot is $500,000. And that's what we're going to compare here. So 1,000. And so since our data set only consists of 2 columns, this linear regression is going to give us results that are the same as our training set when we pass in the training X values. But if our training data was like more diverse and scattered, then our model would not necessarily return the same values for our X's when we run the model against them. It might give us something with like some amount of error. That would be like more of a normal thing. But so anyways, the prediction we're making here is that doesn't exist in our training data is this here for 1,200 square feet, $340,000. Okay, so the next thing we want to do is it says here, you can show the progress of gradient descent during its execution by plotting the cost over iterations on a contour plot. And remember, with our contour plot, the goal is for our cost to be depicted by some point at the center of the contour. Before we do this, I'm going to take a quick break for about 5 or 10 minutes, and then I'll be back. I want to thank you for coming and joining us, by the way. And while I take a break, grab a snack, and then I'll meet you back here. Hey, thanks for sticking around. Okay, let's go ahead and jump back into this and try to wrap this up here in the next like 20 minutes, 15, 20 minutes. We've already been streaming for about an hour, so don't want to hold it too long. Okay, so we're going to be pulling off this, we're going to be basically calling our subplot again, and we're going to be pulling off a figure and whatever this AX thing is. That. Like I said before, this part, the code of this part doesn't really matter because this is utilizing some utility functions that are provided by the course. What's really important is that we just understand what's going on in the plots here, not so much like the creation of the plots. Okay, so there, and then this is our line to create the actual plot for the contour. Passing in our X training data and our Y training data, our parameter history, and whatever this AX thing is. Fig size equals. Okay. Okay, so let's see what this is doing here. When weight is, I know the weight is not exactly, let me do something here to make this a little easier. I'm going to print out this here, just so it's like co-located with this, to make it a little easier for us to know what's going on here. Okay, so we know that the weight is the first thing going on here, and the bias is the second one. When our weight is like near, let's see, it's near, it's like not 200, but it's like really, really close. And our bias is not 100, but it's really, really close. See here. So these are, we know that based on our gradient descent. Oh, there comes the fire ambulance. Gosh, this I would never do a live stream at 4 o'clock ever again. I feel like this is just like going into like traffic time or something. This will never happen again, so sorry. Okay, so we know that these two values here for weight and bias, these are what gets us to a cost of 0 based on our gradient descent function. And then that's what's being depicted here. So remember with our contour plot, the closer you get to the center of these like concentric ovals, then the closer you are to your local minimum. In this case, our local minimum is just like right here. And these arrows are pointing in the direction of this local minimum. So contour plot for the cost versus bias and weight with path of gradient descent. Gradient descent is moving from this extremity all the way down. We're starting our, we're initializing our gradient function with a value, with the value of 0 for both of these. So you can see here that it really starts here. This is where our gradient descent starts, right where this tail of this first arrow is. It's going to start here with this initial value, and it's going to move towards our cost, our minimal cost. If I change the initial values, you'll see that the position of these arrows change. So I'm going to do that real quick. I'm going to make these, make this 100, and make this one 50. I'm going to run all these again, and then we'll see they should not line up where they are right now. It's basically, we should see a difference there. Run all. So see here, now it's like here because the weight that we initialize is at 100, and then the bias that we initialize is at like 50? Doesn't look like 50. Oh wait, my bad, I'm looking at this dash line. It really is here. So 50, yeah, it's like right here. Cool, so I'm gonna reset those back to what they were before. Just wanted to kind of show you that that diagram is just communicating multiple things there. Wish there was a shortcut for run all. I'm sure there might be, but I don't know what it is. Okay, so the above contour plot shows the cost over a range of weight and bias. Cost levels are represented by the rings here. You see the numbers here with the lines, with the rings here, they're colored. Overlay using red arrows. Okay, we just talked about that, so we're gonna go ahead and move on. We can see that the final steps of the gradient descent. When we zoom in here. So I'm gonna go ahead and copy this over, since this is like proprietary code, not really necessary for this little demo here. So let's see, what is this doing here? This is just zooming in. Oh, okay, I see what's happening. So you see how these numbers like really large, and because they're so large and starting out with such large costs, you can't really get in there and see exactly what's going on. And this is not a perfect line going toward the minimum. This line here is not perfectly straight, because if it was perfectly straight, that would mean that we're making like a linear progression toward our minimum, and that progression is actually curved like this, because there are larger steps at the beginning of the iteration, and then there are smaller steps toward the end, closer we like converge towards the lowest cost. So as we zoom in here, you can see how this actually curves in. That's what we're saying here. The distance between the steps shrinks as the gradient approaches 0. Okay, so now we're going to increase our learning rate. The learning rate is alpha. As I mentioned before, the learning rate is going to determine a lot. It's going to determine the size of those steps between each of the iterations, and having an alpha as either too small or too large can have consequences. In the notes here, learning rate has a big influence over the efficiency of the gradient descent algorithm. When the rate is too small, our algorithm is very slow because it takes more steps to actually get towards the lowest cost, or the minimum. And then when the rate is too small, actually should be large, not small. When the rate is too large, this is going to increase the cost, but it will potentially overstep the minimum, because we need it to be like fine-tuned. And not only will it overstep the minimum and like going like way past it, it'll actually potentially begin to diverge as well. So we need to have the right alpha, and then we're going to just like play around with that real quick. So we're going to initialize the parameters again. So initialize the weight at 0, initialize the bias at 0. Then we're going to set alpha to a large value. And then we're going to do iterations 10. Alpha is going to be I don't know what 8. I'm really bad at like reading scientific notation and doing it in my head. Okay, so this is going to be, 0.8 is going to be what we're subtracting. We're going to be doing 0.8 times the derivative of the cost function for our weight and bias. Okay, so, and then we're going to run gradient descent. And it's essentially going to be what we had last time we ran it, so I'm not going to bother to type that out. I'm just going to go ahead and copy that. Oops. And did I forget something? I'm going to run all of these real quick just to make sure something's not weird. Oh, I didn't get all of it. Let me fix that. There's 2 lines here, I only got 1 line. Okay, so there we go. And you can see here that as, oh wait, I think I should probably rent Yeah, I should probably print this here. I want to see what the final is. We're gonna depict this visually as well, but I just want to see what happens if I print out the weight final and the bias final. It should be something that it looks weird, I'm assuming. Yeah, we're getting like really crazy numbers here. These numbers mean that we've diverged these here. Yeah, like this is, I mean, I guess it's possible if we have like a really messed up, I don't know what situation these numbers would make sense, but I'm not going to discount it. I just know that for what we're doing, these numbers don't make sense because there actually is a minimum of 0 for sure that we know. But this is what happens when your alpha is just not correct. It's when it's just too large. Okay, so so above, the weight and the bias are bouncing back and forth between positive and negative. I'm gonna go ahead and just show this before I read that description, so it'll make more sense as I read through it. So we're gonna pass in. This is gonna be a diagram that shows what divergence actually looks like. So I'm gonna pass in the parameter history. We're gonna pass in the cost history, X training data, and then the Y training data. Okay, so it says here, above, the weight and bias are bouncing back and forth between positive and negative, with the absolute value increasing with each iteration. Further, each iteration of the derivative of our weight and our bias cost changes sign, and cost is increasing rather than decreasing. This is a clear sign that the learning rate is too large and the solution is diverging. So basically what this is saying here is, if you see here, the first step of this, so each time it goes back and forth like this, these are the different steps, right? So in a normal situation, you would expect that the cost follows this parabola, which is the actual correct configuration for alpha and weight and bias, this blue line here. But what we're getting here, because our alpha is too large, is we're making a giant leap over, and so it's actually going from a negative value to a positive value here, to a negative value, to a positive value, and it's not settling on the actual minimum. Instead, it's settling on some like crazy number that is like way outside. One thing though is like, am I looking at this backwards? So the first value that we're getting here, this is 65. One thing to note too, with our iterations, if we were not limiting our iterations to 10, this would keep running like until we just ran out of memory or until something happened. I don't know what would happen, but it would just keep going, because divergence just means that it's just never going to have a output that suffices for the algorithm, unless we do that. So it would just keep, the number would just keep getting increasingly large in either the positive or the negative direction. It would just keep bouncing back and getting larger. That's what divergence means. And that means the cost is going to continue to increase as well. So actually, I was thinking about this wrong. I was assuming that this is the start, and the start is actually if I zoom in here, the start is actually down here. When our weight is at 0 and our alpha is too large, it just starts to bounce back and forth and go up there. And then here you can see when we're doing it, when we're depicting both the weight and the bias with the soup bowl plot here, it's same things happening. It's when the bias is 0 initially here, and then the weight is 0 initially, our cost is up here. So it's bouncing back and forth and our cost is increasing. I think one thing that this diagram should have that would make it a little bit more evident is have directional arrows that would show the direction of the increase of cost. That's my only criticism for this, because I think it could be a little bit misleading if you were not critically looking at it. But that's neither here nor there. I think we are actually done. So this has kind of been the purpose of this video, is just to get this done. Now, I'm still on the fence about whether I'm going to follow up and do a review over this whole thing, just to kind of like put it together in one concise video. I said I was going to do it, so I think I will. I'm not going to tease too much. I just don't know when I'm going to do it. So go ahead and like, comment, and subscribe. And then you'll be able to get some type of notification. Push the little bell icon. That's what they say these days, right? They say you're supposed to say like, comment, subscribe, and push that bell icon so you can get the latest notifications whenever a new video goes up. That's what they tell us we're supposed to be telling y'all when it comes to our channel. So do that. Go push the little bell and everything. I'll try to get that review video up sooner than later, to be completely honest with you, because I don't want to linger on it too long. So expect that sooner than later. And then I'm going to go ahead and start the next section of this little series. Let me see what I have coming up next. That way you can have a little bit of insight. Give me just 1 second to pull up the course here. Uno momento, por favor. Uno momento, por favor. Okay, my courses. Okay, so we did the cost gradient, or the gradient descent. The next thing that we'll be talking about is doing multiple linear regression. That video, well, at least getting started on that, is going to involve 2 different lab sessions. We're going to be doing some like stuff with NumPy and vectorization. Then we're going to be doing multiple linear regression stuff in Python. Expect to see those probably like this Thursday. Earliest by Wednesday, latest by Thursday, and definitely by Friday. I'm going to try to get all that done this week. So stay tuned. Love seeing you around. Love having you here. I don't know if in the future videos I'm going to spend as much time manually writing out these notes live. I might just come into this having this stuff kind of like prepared, like the notes part, the markdown part sort of prepared. That way we can just jump into the code and not have to do so much like fiddling around. I don't think that that's providing a whole lot of value. But if you want to get to the meat of these, remember that you can go to the videos that have like the designation term explanation on them. Those are going to be the most useful if that's what you're here for. Other than that, don't forget to check the resources in this video description. I have some really great links in there. That list is going to continue to grow so that you can have as many resources as possible. Many of the things that I'm posting in there are also free. Actually, right now, all of them are free for your little journey. And if you need help or anything, just let me know. Go to my link tree or reach out to me on LinkedIn or any of those. I'm always here to help. So with that being said, thanks for coming by. I'll catch you on the flip side. Adios.